So first of all, 5G will enable the convergence between broadcast and broadband technologies. So it will enable higher bandwidth, higher capacity, and lower latency. In a way, the actual solution for streaming is based on HTTP adaptive streaming, which is a protocol based on dividing the media stream into media segments with a fixed duration. And this is the standard used from the media industry. Since it is an HTTP-based protocol, then it will let to stream to every kind of devices. Then it let also to scale our solution, since all the network architecture now is based on HTTP. Moreover, it will let to display the stream of every type of final devices with heterogeneity in display. Anyway, the adaptive streaming has some problems, since if we deal with low latency, since they used to split the media content into segments ranging from 2 to 10 seconds, here the problem is that it will cause a delay in the order of 10 seconds. So it is a latency which is too high in order to stream a broadcast live streaming. Then the proposed solution from the industry is based on common media application format. These come with a chunked mode. So Chunked CMAF will let to split our media segments of our video into smaller parts, which are called MP4 fragments. Basically, this is possible by splitting fragment to send just one fragment per time instead of sending all the media fragments. So we can reduce delay, since we are reducing the instead of being the overall delay to be relation with the duration segment duration. It is now related to CMAF fragment duration, which is smaller than the media fragments. The solution that we tested for Chunked CMAF is based on a typical media workflow which deal with Chunked CMAF is based on a video ingest, which is the one who produces the content. Then there is a media packager which is in charge of encoding and creating the media fragments and segments. An HTTP server which will deliver the content, and a dash player which will receive the content and display it. Among these different nodes in our network, the most important media packager and HTTP server, since the media packager, in order to deliver Chunked CMAF, need some modification which deal with some time constraint for live encoding. Moreover, it is necessary that our media packager insert keyframes in order for synchronize our content and in order to be able to be synchronized to the last available media fragments. Moreover, since we are splitting our content in media segments, then in media fragments, our media fragments need to be need to have a MP4 header which will let also to synchronize each media fragments when received at the decoder. On the other side, the HTTP server, in order to deal with the Chunked CMAF, need to recognize inside our media segments each MP4 fragments. Okay, as I was saying, our HTTP server need to recognize the fragments inside these segments. So it is done by analyzing the byte stream of our encoded data. Then when you recognize the media fragments, it can deliver by splitting the HTTP response into chunks, and each chunk of the HTTP delivery basically contains one chunk of the MP4 fragments. Then at the end, dash player receive each of the need to be able to synchronize with the server in order to ask always the last generated fragments, then receive it and display it on the screen. We implemented a Chunked CMAF solution. This is our test bed that we use for our experimentation. From one side, we have on a server, we use a server which basically adds both the media packager and the HTTP server. For media packager, we use a GStreamer framework in order to create an MPEG dash manifest, and media segments contain a variable number of media fragments inside. GStreamer was missing some necessary plugins in order to deal with the Chunked CMAF solution. Then we used these two free repository and modify some plugins in order to create an MP4 multiplexer, which create the MP4 fragments, and another plugin which create the MPEG dash manifest and create the media segments. For the HTTP server, basically we use a Node.js web application, which it basically receive the data from the media packager and check inside the data which are the media fragments, and then send it to the client. From the other side, we have the dash player which receives the content, and it basically is also a GStreamer application. It already have everything in order to receive and display the content. In the middle, we have a wireless access point which let the dash player to connect and retrieve the content from the HTTP server where it is stored. In order to give an evaluation of our solution, we had the following metrics. First of all, since we are dealing with media streaming, it is important to take into account the effect on the user. Basically, each player, when starting to playing the content, has some bufferings. But this rebuffering can also happen during the media streaming, since if the player remains without data, it has to rebuffer in order to start playing again. So visually, this can be seen through image freezing, which can have different durations. So we measure the duration of the freeze that will occur during streaming low latency video streaming, and also the number of these video freezes. Moreover, since we are working on reducing latency, we evaluate also the end-to-end latency, which is basically the time between the time elapsed between the display on the screen and the time it is ingested on server side. It is composed by the time for encoding a package in our content at the media packager. But since we are packaging our content in media fragment, it will also affect the overall latency, the duration of the fragment. Then we have the time for fetching the content from the media, fetching the content from the HTTP server to the dash player, and then the time for decoding at dash player. So basically, the end-to-end latency is the sum up of these four components: time for encoding, time for of the MP4 fragment, time for fetching, and time for decoding. The dataset that we use is the big Bug Bunny video dataset. We get a raw version of this video and encode it in 6 different representation, ranging from 1.2 to 8 megabit per second at 30 frames per second. Then, since we want also to evaluate different configuration for fragments, we create fragments of different duration. So basically, we encode our content using a different group of pictures. Then, depending on the group of picture we use, we can create media fragments containing a different number of frames. Each fragments need to contain at least 1 keyframes in order for synchronizing. Then all the other frames can be P or B frames. So varying the group of sites, we create fragments which has just or just 1 fragment. Then it comes that our fragment duration is 33 milliseconds. Then we have the configuration of media fragments which contain 3 frames for fragments. So we will have 10 milliseconds of MP4 fragment. Then another configuration containing 5 frames for MP4 fragments. So the overall duration of fragment will be 167 milliseconds. Then we also compare with a legacy solution, which basically consists in using MPEG dash with fragments of 2 seconds of duration. So we are creating legacy media segments which are not split into smaller MP4 fragments. Here are our result. In terms of latency, what we have here, there are 4 tables. In the first table, we consider the first configuration, which has just one frame per fragment. In the second table, we have the configuration with 3 frames per fragment. In the third table, 5 frames for fragments. And the last one, a legacy solution with 2 seconds duration. In the second column, we will see the 6 different representation, ranging 1.2 to 8 megabits per second. What we see is that, of course, if you use smaller smaller MP4 fragments, we will have the lowest latency. So we have around 120 milliseconds. If we go to 3 frames per second, it will raise to 100 with around 190 milliseconds. In the third configuration, which use 5 frames per fragment, we will have around 260 milliseconds. And in the last one, which give us the worst result, of course, we are in the order of 2 seconds, since we cannot have a lower latency than the segment duration. So what we can see from this table is that, of course, the fragment length severely affects the overall latency. Dealing with freezes, what we can see is that the evaluation here is a bit different, since a smaller fragment will cause a great number of freezes. So we are ranging from we are around 30 freezes if we are in the case of 1 frame per fragment. Then if we pass to a configuration with 3 frames per fragment, we will the number of frames will be lower, around 10. The same for 5 frames per fragment. While in the last case with 2 seconds of segment, we will not have freeze, since we will have a higher buffer at the receiver, so we have 2 seconds of buffer, so we are not getting our image will never freeze. We can see it graphically, which basically the first configuration, which has just 1 frame, has the worst performance, while the last one has the better one, because it never freezes except for the highest representation. In the middle, we will have a trade-off between the 2 solutions. We will have a higher latency, but less number of freezes. Okay, so we get the following conclusion. Chunked common media application format, of course, reduce latency compared to legacy solution. Anyway, it has some drawbacks, since a reduction in delay may cause image freezes, which will affect the quality of experience of the end users. So it is necessary to find a good trade-off between these 2 metrics, the latency and the image freezing. In future work, we would like also to improve our delay chain by introducing other new nodes, which can be content delivery network, the core network, or also introducing some other new technologies, such as some edge computing server at the edge of the network. Both this solution can help to reduce latency and also to reduce network congestion.
you.